What you're looking at right now is just me talking to you, but with an autostereogram or magic eye shader effect applied. But how do autostereograms even work? How can you make one in a shader? And could you even play a game with this effect on? To warm up, let's do the easiest version of Magic Eye possible. Hold your fingers out like this in front of you. Now look at something beyond your fingertips, play around with the distances a bit, and you should see a third finger floating in your peripheral vision. Magic Eye is based on the same thing. Here we have a row of dots. Normally when we look at something, our eyes will converge so that both retinas will see the same image. Now if your screen was transparent and you could look at something beyond it, your eyes would rotate outward slightly to focus at that new distance. This is called divergence.
You blur your eyes like you're staring straight through the picture, and you keep your eyes unfocused. And then...
If you do that right, each eye will receive the image of a different dot. Because the dots look the same, our brain will interpret these two images as one dot that is further away. This effect would happen for each dot in the row, so we would see a full row as if it were further back. And there are actually a lot of patterns around us that can cause this same effect. That's how David Brewster discovered the wallpaper effect back in 1844. Now let's add two more rows of dots. The red row will have dots spaced farther apart, and the blue row will have dots closer together. If we stare beyond the screen, what we notice is the red row seems further back than the green row, and the blue row seems closer to us than the green one. So the spacing between elements in the pattern, the repeat interval we'll call it, controls the depth or how much things pop out. Even in a single row, by changing the spacing between some of the dots, you can create the autostereogram effect of different dots popping out. The tricky part is understanding that if you want just one dot to pop, you have to reduce the spacing between that one and the one before it, but you still need to move all the other dots after it to keep their original spacing. Our goal is to take this idea and apply it to each pixel in a repeating image instead of just repeating dots. The pattern has to be complex enough so that shifting pixels results in visible changes everywhere. So instead of just a row of dots, we have a row of repeating pixel patterns. Yeah. If we select an area of the pattern, like this rectangle, and we want the pixels to pop, we need an algorithm that will shift all of those pixels in that rectangle and beyond to construct the repeat intervals we need in the image. I did things the wrong way first. I went straight to the GPU to try and have every pixel check for depth and shift without considering the repeat interval at all. It was a learning experience, but let's instead just ease into this with the most understandable method. What the Photoshop method shows is interesting. They use a silhouette to signal depth. For each pattern slice that has depth, they make a copy of just what lies inside the silhouette for that slice. Then they shift that copy to the left 5 pixels. So they reduce the repeat interval between that part of that slice with that part of the preceding slice. After that, they duplicate the same shifted slice to everything to the right. Do you see what that does? That's saying, if the repeat interval was shortened somewhere, we need to make sure to maintain at least that original interval after that, just like we do with the dots. Then they do the same process for each new slice as they move to the right, which means for every slice, they may already be starting with some shifted pixels, and they shift them more, and shift all the others more too, since they duplicate the current slice. That's the gist. From the Wikipedia article, which I'm pretty sure is talking about the CPU implementation, it's just like the Photoshop version, but it's done pixel by pixel, from left to right in each row. So we can start with a repeating pattern. I've colored each slice of the pattern differently to help us see them. In this simplified example, we take one row of pixels and number them from 0 to 4 for each pattern slice. So the slice width is 5 pixels. Starting from the left, we step the full width of a pattern slice to our right, landing in the same pixel in the next slice. Then we check the depth in that new slice. If there is no depth, we take another step to the same position in the next slice. If we land in our rectangle of depth, we take a small step backwards and draw our pixel there instead. That reduces the repeat interval between that pixel in this slice and in the previous slice. After that, we try to step the full width again. Notice now, stepping full width, we remain behind where the original pixel would be. We again check for depth. If we find more depth, we take another small step back to keep the reduced interval. If we continue this way for each pixel in the first slice, from left to right, in each row, we'll end up with an autostereogram. Now that we understand how it works on the CPU, we can tackle the GPU. Since on the GPU, pixels can't write data to other pixels, we can't just shift the data of the pixel to the left. Instead, we have to work backwards to find out what data should end up in this pixel's location. For example, pick any pixel. If we step to the left by the pattern width, we end up at a pixel in the preceding pattern slice. If there is depth there, then on the next step, we shorten our step. And this is the same as saying a pixel that would arrive here with this depth would have to have come from a shorter distance away. If we keep following that logic back to the first slice, we will end up at the pixel that would have come to us on the CPU. And here's the result of this basic autostereogram we've been working on. View it properly and you'll see a rectangle popping out of the pattern. Here's another inspired by the Wikipedia article showing 3 rectangles at different depths. The lighter the shade, the more the rectangle should pop out. With multiple levels of depth, our algorithm has to change slightly. Instead of each pixel shifting a specific amount, if it's in the depth area, now it has to shift a percentage of the maximum based on the shade. We call that maximum the depth factor. So the lighter the shade, the shorter the repeat interval, and the more things pop out. Here's the full code for the algorithm, and as you can see, it's tiny. I use frag chords directly, which means we need to scale them down before sending them to the sampler. After that, the repeating of the pattern is handled by the sampler. Once I got that version working, I tried this ray marched scene. It shows concentric rings mid-spin around a sphere, which I used as the depth map. For an animated magic eye effect, let's try animating this ray marched scene I'm already using. At least for me, it's hard to make out anything because all the other repeating patterns distract me from the illusion. The way people fix this is to randomize the pattern each frame. We can do that by adding a hashing value that changes each frame and each pixel to our UV coordinate. The most intuitive pattern to use here would be a random noise pattern like this, but I actually find it easier to see and easier on the eyes using one of the more organic ones. I realized then that I could make the depth pop out way more by increasing the depth factor. The more I crank it, the more depth I perceive. At 70, it basically jumps out of the screen at me. We can't shift more than the width of one pattern slice or the algorithm won't work, so I figured I could crank the shift up to 100 on my brand new Lenovo laptop. Look at this. Look at this on my brand new Lenovo laptop. It's broken. Oh, what's going on? Look at that. What happened? As you can see, not only did that break the shader, but it broke all the graphics on my brand new Lenovo laptop. Thankfully, restarting my laptop fixed that. I know the reason for the crash was that I was using a while loop, but I'm still not clear on the specifics. I also don't really want to test it anymore. The simplest solution is to use a for loop with a high enough end condition that ensures that it can step all the way through the image, and to be safe, I've lowered the depth factor. Two major issues I have with our current animated stereogram are, it's a bit hard on the eyes, and they also alienate anyone who experiences seizures from flashing light. If the whole point of scrambling the texture is really just to eliminate the appearance of the repeated shifts, then can we use a texture that moves each frame but in a more natural way? I experimented with a repeating and seamless Voronoi number pattern. It works quite well. Another benefit of using moving patterns instead of just noise is that your eye can find the proper focus using the pattern itself instead of relying on dots above the image. This is still shifting the individual pixels of the Voronoi pattern though, which is why there is still some warping going on. I'm working on a way to have the actual Voronoi cells shift, which would be even more unique. Now for the main event, playing a game as an autostereogram. The only other example of this I know of besides mine is a Magic Eye version of Doom called Omdo. For this video, I'll be using the Resident Evil 4 Remake Chainsaw demo. I'm using Reshade, which is a post-processing injector. If a game has a depth map in its pipeline, Reshade can usually make it accessible to us. Our stereogram will depend on that. So how playable is this? At the start, you can make out Leon easily. Also to the right, there are some branches that come through, and to the left, there are boulders. I used the boulders as a point of reference and rotated the camera until they moved from my left side to my right side, so I knew I was facing the other way. I walked in that direction until I heard a car, and I could make out the frame of the car. Okay, back to the start. If we walk straight, we come to a signpost, a very pointed signpost, and it's very easy to make out. If we go right at the fork, there's a clearing with wooden boards to the back of it, which are easy to see with Magic Eye. Then there's a gate you can kind of see and definitely hear the metal piece of it when you walk on it. Then you hear flies from the dead carcass, and there is an upside down U of trees over it. Then a blockage you can see and need to crouch under to get through. Then there's stairs to the house. Then the first cutscene.
Sorry to barge in like this. Busco a polícia. Vino aqui?
You can see Leon and sometimes the other guy. Then my first encounter where I actually had to fight. I did some of it with the depth map on, but I had aim assist on as well, and I got enough shots to kill him luckily. Then outside the house again in the daytime, there is a bridge, and we can make out the posts, which are enough to know how to cross it. Later there's a fallen tree that we can see and crouch under to pass through. So far I've shown you how we can navigate an environment with extremely poor vision. For some games that might be enough. With Resident Evil, on the other hand, here is a more realistic scenario. So there are about 10 of these Las Plagas zombies and we have to keep them at a distance. So let's try that with just the depth map on. Okay, so I can barely see anything, but I can run around these guys since they are slow. Still, if you aren't careful, you'll get caught. So now let's put Magic Eye on.
Next.
I can only see Leon and maybe bits and pieces of other people right as they're lunging at me. Then I can't even see them when they have me because there's just too much at once on the screen. I can't see enough of the terrain either to navigate, and game over. So you might think there's no way to play this full game with Magic Eye. However, did you know people play games like this blindfolded? One of them is with assistance, meaning one person tells them what to do
Fire.
and the other does it without seeing.
Left. Fire. Fire. Right.
So for example, they pause the game, then they unpause, quickly adjust the cursor, and then pause again, get more instructions, unpause, quickly adjust the cursor and pause again, etc. until it's lined up for a shot, and then they take the shot. So I tried pausing to get a clearer view under the Magic Eye effect. And that helped, but it wasn't enough. So I looked at how I was calculating depth and I realized that I could adjust the depth so that the brightest point, the point that's in focus, was further away, meaning we can see people from further away. So we can keep pausing and scanning like that, or we can make the shader continuously sweep the area and see if that helps us see better. There's some really interesting ideas, and I think there's a potential speed running category here. If you want to see a longer video of me playing Resident Evil 4, with this effect on, or if you want a copy of the Shadertoy and reshade code to try on your own games, you can find those on my Patreon. It was very cathartic to go from being one of the I don't see anything people to one of the I made this work on a video game people. I hope some of you give this a try because it's super satisfying. Also, by exploring this idea, I learned how easy it is these days to generate depth maps for different things, and there are many possibilities here. You can use it to apply lighting to a scene using a depth map, you can use it to create a depth of field effect, and I'm excited to experiment with depth maps in my Painterly shaders and ASCII renderers and falling sand effects. Thanks for watching, and I'll see you in the next one.